We've said that c is the speed of light, and I've pointed out that that is the speed of light in vacuum. And when light travels through different material, it actually is going to slow down. And when I say material, you might see the term medium, same thing. And obvious examples to talk about with light would be glass or water, perhaps, plastic maybe. To talk about light traveling through lead isn't particularly interesting because you know that lead is not opaque. Light doesn't succeed in traveling through it. So we usually talk about opaque materials when we talk about light traveling through something. So there's a quantity we call the index of refraction, and we use the letter n to represent that. N is a unitless number, so it doesn't have any dimensions, and it's going to be greater than 1. Vacuum has an index of refraction of exactly 1. Not rounding to 1, but it is defined to be 1, perfect vacuum. And the idea being that it's the ratio between the speed of light and whatever you have in your medium. This is frequently the way you're going to see it, that the speed of light in the medium you're in, or the material, is c divided by n. So for vacuum, that's just c divided by 1, so you get c back. You can see for air, it's really, really close to 1. So normally if we talk about light traveling or any type of electromagnetic radiation traveling in air, we just kind of assume it's the same as vacuum. But once you're up to water or glass, it actually slows down a lot. So the speed that light travels in water is actually quite a bit less than it would travel in vacuum. Now, we're not going to go into the origin of this. The origin of this actually has to do with the electromagnetic waves, that is light, that is a light wave, polarizing the media, and that polarized material then interacting back with the electromagnetic wave. So we're not going to go into details on that, but this is kind of interesting to understand and to think about. So light travels slower in a material that is not vacuum, and it is due to an electromagnetic interaction we're not going to talk about, but you just need to look up what the index of refraction is for these different materials to get the speed. Now, we are briefly going to go into one of the consequences of this, which is interesting to think about. Refraction, so how light bends, is also a consequence of this. And something that I avoided putting in a couple of slides, but I at least have to mention, is that there's a very interesting phenomena called Cherenkov light, or Cherenkov radiation, that relates to this phenomena. And that's actually one of the things that I study, is how we can use Cherenkov radiation to actually understand cancer treatment with radiation. So Cherenkov light is cool and connects to all of this, so the index of refraction is something I get really interested in, and I think about, for instance, can we make better detectors for cancer treatment using these phenomena? So it's one of my favorite things. So within the scope of this class, what do we actually need to know? We need to think about how the wavelength of the light is going to change as it goes into a different material. So remember that we said that there's a relationship between speed, wavelength, and frequency. So we can write this as wave speed is going to be our wavelength divided by our period, or wavelength times our frequency. And if you rearrange that, you get that your wavelength is equal to your wave speed divided by your frequency. Now remember that the wave speed is determined by your medium, your material, and the wave frequency is determined by your source. So when we first introduced this, we said, hey, pay attention to the fact that wavelength can therefore change if your medium changes. So if we have a light wave that is initially in vacuum, it has some wavelength. And if you say, well, what is the frequency of this? Well, that depends on what the source defined the frequency to be. So we have a certain wavelength due to the frequency and the fact that it's in vacuum, so we know what our speed is. But then it enters something new. So for instance, glass. Maybe it's going through the window of the space station. Now it has an index of refraction, n, which means it has a new speed. It has slowed down. The frequency remains the same, and so if the velocity has changed, if the wave speed has changed, and the frequency remains the same, then your wavelength must change. And so you see that picture here, that the wavelength is longer here and shorter in this glass. It then changes and goes back to what it was originally. So notice that this is a picture in position. So when I say, oh, the frequency stays the same, well, we don't literally see that because we're actually seeing a picture of position. So that's the consequence of this, is that we can talk about the wavelength changing as light, for instance, is in water versus glass to air. And this also is going to have an impact when we study lenses and think about how light bends as it passes from air to water and vice versa.